Hello, y'all. Matt Roscoe here at the University of Montana in our Math 133 course with a short lecture on volume. And let's just pick up where we left off, um, or I guess review where we left off. What I had you do in class was to build prisms, each with a volume of 24 units cubed. And we were able to generate this table of examples. The area of the base was recorded for each example, and the height was recorded for each example. And what we see is that the area of the base times the height is equal to the volume. And so we can generalize that and say, well, the volume of a prism can be thought of as the area of the base times the height. And this really makes sense in terms of what we know about the definition of multiplication. The area of the base is really a group. It's how many are in each group, and then the height tells you how many groups there are stacked on top of each other. So number of elements in a group times the number of groups gives you the number of elements total. But we immediately recognize, though, that the area of the base is nothing more than the length times the width. So we brought this question to task. Why not just use length times width times height for all prisms? And the answer to that is because if you think of the prism as volume being calculated the area of the base times the height, then you can extend it to other solids whose cross sections are all, I guess, congruent or equal. And so here's an example, well, let's just state Cavalieri's principle, the thing that helps us. It says that when two solids, each with a base in the same plane, have equal volumes, if every plane parallel to the base intersects the solids in cross sections of equal area. So we can see that this top and this top are in the same plane, this bottom and this bottom are in the same plane, and the cross sections, which are taken in a parallel plane, if this green area is equal to this green area, then we would assume that the red and the blue figures would have to have the same volume, because everywhere we cut them, we get something that's equal in area when we cut them parallel to the bases. To understand this a little bit better, I showed you an example of an applet I made that the picture is actually taken from. So the idea is this: we have these planes that are cutting each of the solids at the same level. I can show the plane there, so the plane sort of rises and falls with the cut. I don't like it around, so I'm going to get rid of it. But the idea is that if the red base and the blue base are exactly the same in area, if those two bases are the same in area and they extend everywhere at this, at every height, they're exactly the same, because these are both prismatic-like objects that have equal cross sections. Well, then we would theorize that, Cavalieri theorized that the blue and the red have to be the same volume. We could change, of course, this idea, make the red area a little bit bigger, maybe make it some sort of a rectangular prism. But then, of course, the blue area would have to go up as well, the blue basis area. So again, if those two green areas are exactly the same, and every cross section shows the two equal areas, then we would think that the two things would be equal in volume. So kind of fun to play this, actually. If you just animate it, we can just watch it move by itself. So that's the idea of Cavalieri's. If cross sections are all of the same area, then the volumes would be the same. So we extended this to think about cylinders, and we said, well, if we can kind of think of the volume of this red prism as the area of the base times the height, and the volume of this blue cylinder as the area also of its base times its height, if the two bases were equal here, right? So if this is area of base times height, then this one would have to be area of base times height as well. But here we know the area of the base to be pi r squared, so a volume formula for a cylinder should be pi r squared h. And indeed, that's what we formalized. And I think we ended about right here. And the next question that we need to address is this idea of cones. So we think about a cone. Each cone can be thought of as sort of living inside an associated cylinder. So an associated cylinder would be a cylinder whose base is exactly the same. So in other words, a circle of the same radius, and whose height is actually the same as well. So the apex here, the blue cone, is exactly the same as the height of the red cylinder next to it. Let's take a look at what this looks like as an applet. So I'll pull up the applet now. Let's see for the cone. So here's the idea. We've got these two, I guess, these two circles, each of equal area. And if I grab, the idea is that we have, sort of here at the bottom we would have equal areas, right? But as we go up, the circle on the left is getting smaller and smaller and smaller and finally disappears entirely. One thing that might be interesting to investigate is, if we're halfway up like this, would the circle on the left be half the radius of the circle on the right? And I think it would be. So I think it's proportionally getting smaller according to how high above its base it is. But we could prove that. But the idea is that, well, if the green circle on the left is going to 0 as we get closer and closer to the height, and it starts out as the full, I guess, circle of the cylinder next to it, then we would think that the blue cone on the left would be some fraction of the area of the red cylinder on the right. And the question is, what fraction is the right fraction? And that's something that we're not going to prove in this class, but we can investigate it through direct, I guess, investigation of figures. So let's go ahead and take a look at some cones and cylinders under the dock cam. And maybe I'll just pose the question. The volume of cone should be some fraction of the volume calculation of its associated cylinder. So in other words, we know what a cylinder is. It's the area of the base times the height. And the question is, what fraction should we take of that cylinder's volume? And how would we find it? And I guess the way that we can find it, at least for our purposes, is by direct investigation. So let's take a look at a direct investigation here. Oops. Sorry about that. Okay, so what I brought with me over to my office is these things that you saw today in class. And I don't know if you noticed, but it turns out that these are exactly the associated figures that we had shown in the slide previously. You can tell they have about exactly the same radius base, so those circles would be congruent. And when I put them flat on the ground, this is kind of hard for you to see, but the two heights are exactly the same. So that means that we should be able to see how many of these fit into here by simple pouring. And so let's go ahead and take a look. We've got some beans here, the beans that we didn't get to pour in class today. I'm going to try to fill it all the way up and ask the question of how many of these beans fit in the associated cylinder. Oh, I lost a few. I think I lost 4 over there, so I'm going to put those 4 back. Go ahead. So I can kind of see that one pour of the cylinder into its associated cylinder, of the cone into its associated cylinder, filled us up, less than halfway. So I'll try it again and see what happens here. See if I can keep from spilling too much. I wanted to try to be pretty precise about this. Of course, these are beans. So there's 2 pours, and 2 pours doesn't quite get me there either, but it does look like a 3rd pour will make it. So let's go ahead and try one more pour here. And so I'll pour that 3rd one in there. And I can see that when I pour the 3rd one in, it appears that that cylinder is now full. So it appears that the right number of these that fit in there is 3. I don't know if you can see this if I tilt this forward. But you can see it's pretty full now. And we put 3 of these guys in there. So that's a pretty strong argument. I think that the right number here would be some number close to 3. And indeed it is. And this has been proven rigorously. So the big question next might be, well, what about a pyramid, right? I mean, we could play the same game with a pyramid. So let's take a look at the pyramid. And again, we have this situation where we're talking about, a pyramid whose base is the same as a triangular prism of the same height. And so these would be sort of associated, and we'd think like, well, you know, they have exactly the same area of base, but as we get higher and higher and higher, the pyramid's cross sections are going to zero, whereas the prism's cross sections remain constant. So we can definitely argue that this blue volume must be less than this red volume, but the question is how much less? So let's just observe this by filling up some to get some sense of what's going on here. All right, so I'm going to pour out my beans back into my cup, and I'm going to get out the pyramid in the set. This is the pyramid that we have in the set. Let's see if I can open it. Okay, pull out its net. So there's a pyramid. So I'm looking for a triangular prism then that has the same base, and that's this one. So I hope that you can see from above that these guys are almost exactly the same base. You can see if I put one on top of the other, it fits right on top. So the bases are the same. And then from that view, I hope you can tell that the heights are about the same as well. So the question is how many of these fit in there? And let's just go ahead and find out. All right, so there's one. Oh, I spilled a little bit. This is not an exact science, I can tell. I'm going to put about half of those in there because I think I spilled about half of them, and then the other half I think I just didn't pour them carefully. This is again not an exact science. We're trying to just generate intuition. This time what I'm going to do is I'm going to get these out of the way so I know. Okay. Oh. But I know that the ones that I poured now outside of the... So we got that much. I mean, I hope this gives you a sense that we're still not quite there, right? You can see that. So we still have a little bit more to go. Let's try this again. So I'll go ahead and see how it happens this time. And it appears that we've got it pretty much full now. So it appeared that it took 3 of these guys to fill that guy up. And that seems sort of, I guess, to me it seems sort of nice, right? That both the pyramid and the cone have this same sort of feature that factor of 3 relates these two, right? So if we ask this question again, you know, what's the right fraction of the height times area of base, we can answer it by simple investigation. So I guess the big takeaway here is that the volume, let's go ahead and write down what we found. So let's see, the volume of a cone is 1/3 of the volume of its associated cylinder. So I'll put it and we know the volume of a cylinder is equal to the area of the base times the height, and so it's 1/3 pi r squared h for the volume of a cone. Let's see, so what about the pyramid? So the volume of a pyramid is very similar to the volume of a cone. It's 1/3 times the volume of the associated prism, and that would be 1/3 times the area of the base times the height. And now we would probably leave it right like this because, of course, the area of the base can be many different things. For a pyramid, we could have a square pyramid. Could have a triangular pyramid, a pentagonal pyramid. But the area of the base will have to be computed, and of course the height will have to be known in order for you to find the volume of pyramid, which will be 1/3 of its associated prism. I do want to just point out that, the way we've approached these two volume formulas is not really rigorous mathematically, and the rationale for that is, we actually need more high-powered mathematics in order to prove this rigorously. And in fact, this is one of the classic, I guess, results that's proved using calculus, which is of course above the scope of this course. But I think that, giving kids a good sense of, well, where does this 1/3 come from through pouring activities like the one that I've shown on the video here is a great idea, and I would encourage you to do that with your students. So this is an interesting thing. Our last section in the chapter actually deals with spheres, and in order to understand the volume of a sphere, we should probably understand its surface area first. We haven't really addressed that yet, but it turns out that the surface area of any sphere is given by 4 pi times r squared, where r is the radius of the sphere, and this is the same as the area of 4 great circles of the sphere. And a great circle is the circle on the sphere whose radius is equal to the radius of the sphere itself. I want to draw a quick picture just to give you a sense of what's going on here. So let's see if I can sketch it. So if we start with a sphere, we think of the sphere as sort of, something that looks like this, right? So there's sort of a front and a back to it. And if we kind of think of every sphere, there's a radius to it. And that radius is everywhere here from the center, right? So, I mean, the radius could be up here, or it could be over here, or down here. But if we want to think about, the volume or surface area, excuse me, of a sphere, we can kind of think of this middle circle, a circle inside of the sphere that passes through the center. That thing is called a great circle of a sphere. And so let's see, pen. I'll just say a great circle of the sphere. And here the area of a great circle is going to just be, of course, pi r squared, because it's just a circle, right? Living inside of a sphere. But what's neat about this is if we want to think about the surface area of the whole sphere, and here I have to be careful, I'll try to do this as well as I can. So, if we're thinking about the whole thing here, right? And by the whole thing, I mean, this part up above and this part in here, right? All of this, I guess, on the outside of the sphere, all of that would be considered, the surface area of the sphere. So the area of the sphere, we've been told, is 4 pi r squareds. So what you can see is that it's basically, there's a factor of 4 between the great circle and the surface area of the sphere itself. So it's 4 of those yellow circles in there, right? That make up the surface area of the sphere itself. It's kind of fun to think about, right? Because if there's 4 of them, and we think of the middle as sort of slicing, or I guess the great circle is slicing the sphere in half, then what's happening here is 2 great circles comprise, I guess, a hemisphere each. So 2 great circles surface area make up the north hemisphere, and 2 great circles areas make up the southern hemisphere. I know it's a messy picture, but I hope the action gave you a sense of this idea here. So I find this to be particularly interesting, and so interesting I actually made a video about this. It's on my YouTube channel. So let's take a second and watch it. This is the video. I have to apologize that it's a little bit grayed out. and probably even worse in this recording. But the way the video starts is there is an orange, and the orange is placed in a circle next to three other circles that appear to be the same radius as the radius of the sphere of the orange. Here we go. So what I'm trying to show you here is that the orange actually has a great circle equal to each of the four circles drawn. So I'll just end it right there, right before it shuts off, to show you that what I've tried to do here is show that when we peel an orange and we cut up the peels of the orange, that they pretty nicely fit into four circles of radius equal to the radius of the orange, which is some empirical proof, I guess some real world proof, that indeed the surface area of a sphere is 4 times the surface area of the great circle of a sphere, which would be the circle of radius equal to the sphere. So I hope that was a little bit enlightening for you. This is one of the earliest videos I ever made. It has a total of 58 views. Anyway, let's go ahead and head back here and talk a bit about. Now, you should be able to think again about the volume of a sphere, and it should be related again to its associated cylinder. If we kind of think of this again by comparing. So the idea is if these two, I guess the cylinder and the sphere are placed next to each other, if we're halfway, I guess, up the sphere's height, or I guess right there in the middle of the sphere, then the circles would be the same area and we'd have equal cross-sectional area there. But then as we go towards the bottom, the sphere's cross-sectional area is going to 0. As we go towards the top, the same thing happens. So we certainly could say that, well, the sphere's volume will have to be something less than the cylinder's volume. And we already know how to calculate the volume of a cylinder. So we have sort of like an upper bound. In other words, we know it can be no bigger than this guy. And that there's probably some fraction again here, right? So the question is what's the right fraction to impose here? And now one way that we could do this is we could pour beans, right? Again, and what we'd need is we'd need a sphere that would be the same radius and height, so the sphere that would fit right inside of here. That would be one way we could solve this, or at least get a sense of it. But sadly, my folding geometric shape set comes with no sphere, And it would be kind of interesting to see, the sphere would be really hard to fill, of course, because you'd have to have some little hole that you could fill. Um, but it is kind of it seems to stand to reason though that the sphere should fill more, than the cone, right? The cone filled only a third of this, and the sphere seems like it's more volumetric than the cone, but it shouldn't fill, all of the cylinder either. And if the cone was 1/3 of the volume of its associated cylinder, then we would think that the sphere would be more than 1/3 of the associated cylinder's volume. So in other words, if this was a third of this, then the sphere would probably be, I don't know, something more than a third, maybe a half, maybe even more than half of the volume of the associated cylinder. Let me show you one proof that relies on the surface area. So I guess if we were to actually pour a cylinder, a sphere into a cylinder, what we would find is that it actually fills 2/3 of its associated cylinder. So I guess what I'm trying to say here is that the volume of so the volume of a sphere is 2/3 of the volume of its associated cylinder. And we know that the volume of a cylinder is equal to the area of the base times the height, and that's 2/3 of pi r squared h. But here's the kicker. In order for a cylinder to encapsulate a sphere, in other words, for a sphere to sit inside there, then what can we say about the height, right? The height itself would have to be double the radius, right? It would have to be a diameter because the sphere fits right inside there, so there would have to be two radii in there. And so if we take the 2 and move it out in front, we get 4/3 pi r now to the third. And this is the formula for the volume of a sphere. And it turns out that, had we been in class, I do actually have a half sphere, hemisphere, that we can pour water from one into the other. But you'll just have to trust me, I guess, on this video that a sphere fills 2/3 of a cylinder that's of the same radius and height as the sphere. There is a nice way that you can actually prove this using a kind of a slick trick, and I wanted to show you this really quick, and we'll end on this today. So if I start with a sphere, one way we can kind of think of the sphere is, I'm going to draw in here a little bit of an equator, I guess. Okay, so let's see. Let's see if I can draw this. We can think of a little tiny, let's draw it in green, a little tiny sort of pyramid that comes out here, right? And let's sort of draw it like this. Except for I wanted it to be in the middle. I don't like the picture. Let's try that again. So picture a pyramid that starts in the middle and there, that's a little bit better. So a little pyramid that starts in the middle of the sphere and comes out here, right? So let's talk about the volume of that green little thing, right? Okay, so we know that the volume of a pyramid is equal to 1/3 the area of its base times its height, right? Okay, so that's 1/3 the area of the base, and its height here would be this distance here of the sphere, which is actually a radius. So it's the area of the base times the radius, right? Um, but this is, of course, just one little piece of the volume, right, of the whole sphere. Um, so let's see. If we wanted to get the whole sphere, we'd have to produce a whole bunch of these, let's say a lot of them that were all skinny and just fit together just right so that when we pushed them all together, they made up a sphere, right? And what would happen there is that we get, you know, we get 1/3 the area of the base times the height, the radius for the first one, right? Plus 1/3 the area of the base for the second one times the height, which is the radius. Plus, let's say we did 100 of them, plus 1/3 the area of the base of the 100th times its height radius, right? So there's, let's say, 100 of these that fit together. And I don't know if you noticed, but there's something we could factor out. We could say, well, we could have 1/3 um, the radius and factor that out, and we just have then area of the base 1 plus area of the base 2 plus all the way up to area of the base 100, right? So in other words, I'm just factoring out the 1/3 r from each of the pyramid's expression, and what it leaves is a whole bunch of areas of bases that are being added together. And now I would just ask you to think for a second, what is this thing better known as? So the area of the bases, you know, that's these little parts right here of all of these, let's say 100 or so pyramids that we are summing together. So let's just give you 30 seconds to think about what could we substitute out and recall, you know, name this. Well, if you said that's really just the surface area of the sphere, you're right. You know, the area of all of these bases add together to make the surface area of the sphere, and we know that the surface area is equal to 4 pi r squared, which simplifies, of course, to 4/3 pi r cubed, which is, of course, the volume of a sphere. So I prefer this derivation. I really like it. I think it's really neat. It gives you an intimate understanding of how the surface area of the sphere is related to the volume. It's just the base of all of those pyramids that make up the sphere. Of course, some will argue that, well, you know, that's not really a sphere at all because all of these bases are flat, right? But if you want, instead of doing it with 100, we could do it with 1,000 different pyramids, right? And make those bases very small, or, you know, much smaller. So now it's a 1,000-faced soccer ball. And in fact, we could make it with an infinite number of these pyramids. And if you made it with an infinite number of pyramids, then I think that you would agree with me that now we're very, very close to a sphere, because a sphere can be thought of as an infinitely sided solid. So I hope you like that derivation. I really like it. I think it's a mind bender. And now you know how to find the volumes of all the important, I guess, solids in elementary school mathematics. And I look forward to receiving your homework when I get back from my trip, and have a great spring break, everyone.